Okay, welcome everyone. So what happened last time? I guess everyone still remembers. We introduced the sort of like a little bit of glimpse of gradient descent method, essentially, which is the most and the only method that really is out there in continuous optimization. And somehow we just, very quickly worked out, how it works, like how you can apply it to get a algorithm for max flow. It's not a great algorithm for max flow, but it is an algorithm for max flow. But as you remember, last time, there was one important primitive that we sort of like swept under the carpet. Essentially, we didn't talk about how to actually compute this projection on the space of unit ST flows. It specifically boils down to computing electrical flow, which boils down to solving linear systems. Okay, so essentially what I would like to talk about today is how to solve linear systems fast. And by the way, as Sasha said, there are notes online. And actually, I also uploaded the notes for today's lecture, and they're actually probably over complete. So that's great because you can just read it, and maybe you don't even have to come here. So but yeah, since you are here, let me just talk about it. Okay, so what we are trying to do. So what we are trying to do is just trying to solve a linear system, right? So when you have a linear system, we just think that there is some matrix, there is some unknown vector of variables x, and then there is some target vector b. Okay, and this is the system that we want to solve, and of course, this is one of the most basic things that you do in linear algebra. Okay, so when you have such a system, well, there is a couple of things to think about, but yeah, first of all, how would you solve it? Well, probably the most natural way of solving the system is just to use linear algebra and what we learned in the school. So what you would say that all I really need to do is just to take just multiply b times the inverse of the matrix A, and I'm done, right? That essentially gives me the right solution. So this definitely will give us a right solution, but this will not be a satisfying solution in terms of running time. So it will be the right solution in terms of algebra, but will not be the right solution in terms of running time. First of all, computing inverse is very expensive. Okay, so computing, well, the inverse, essentially the best algorithms, asymptotically the best algorithms we know run in n to the omega time, when omega is something like 2.37, well, something like that. Some number that is strictly smaller than 2.4, but is much larger than 2.3. And so first of all, this takes super quadratic time, which is very bad if we want to get anything efficient. And more importantly, this actually is also not really practical algorithm. Essentially, in practice, the constants there are the hidden are so huge that you would need humongous matrices to get to see any improvement. So Strassen algorithm gets a little bit, like sometimes it is practical, but these things are definitely not practical at all. So what people actually use, they use Gaussian elimination, which actually runs in cubic time, and that's essentially really the running time of these methods. The problem there is, okay, so this is one problem, that the running time is large, but actually there is even more problems with this method. So the other problem that is in this method is actually numerical issues. Essentially, well, when you compute inverses of anything, in general, yeah, we like to assume that computers can manipulate the numbers up to arbitrary precision, but in practice this is not the case. And the moment you are starting to divide by something very, very small, then you get a very, very big number, and then you have to truncate it, and then things become quite bad very quickly. Okay, so there is a whole field of numerical analysis that tries to do something about it, but in general, the best way to avoid it, well, the best way to deal with it is just not even try to do it. And somehow, so that's another reason why this is a bad thing. And actually, there is also one more reason that somehow will become more apparent later on when we actually want to apply these things, is essentially the running time. So essentially, the running time of this method does not really take advantage of the sparsity or structure of the matrix. Okay, so it doesn't matter what your matrix is. it always will take you n to the omega time. Okay, there is no way of getting better running time if for instance, your matrix is sparse. If only like, linear, like sort of O of, so the matrix is n by n, so it has n squared entries, but it could happen that you have only like O of n entries actually non-zero. So you would expect that things will become better then, but somehow this doesn't seem to take advantage of it. And in particular, what happens is that even if I have a sparse matrix, also its inverse can be dense. Essentially, it can have, omega of n squared entries, so essentially multiplying by it will take you n squared time. So essentially, you really don't know how to gracefully take advantage of your matrix being simple. So lack of, utilizing sparsity. Okay, so this is, but this is, the classical way of doing things. And so what we will do instead today is just try to do it, in a different way. And sort of what we will try to do is, instead of trying to, so usually these methods are called direct methods because they just like get the right solution in one shot. What we will try to do instead is just to do iterative method. Okay, so what iterative will mean here is essentially we will start with some candidate solution x0, which might be a really bad solution. Essentially, it doesn't really satisfy the linear system in any reasonable sense. But then we will again have a way of refining this solution, and then refining it again, and refining it, however many times we want, until we'll get to some xt. And somehow what will be happening is that each consecutive solution will be better and better solution. It will be closer and closer to truth. It will never actually ever become the optimal solution, like the actual solution, but it will get arbitrarily close to it. Okay, so this is very much in spirit of what we discussed last time. When we also don't get the optimal solution, we always just can get arbitrarily close, depending on how much time we want to spend on doing it. Okay, and so what will be nice in this model in particular, well, first of all, as we will see, this method actually will tend to be fast, except this is a fast with an asterisk, and essentially the asterisk means that actually our running time now will depend on the numerical properties of the matrix. Okay, so essentially, like for direct methods, it doesn't matter what the matrix is, which is both a bad thing because you cannot take advantage of like simple matrices, but also a good thing because no matter how bad your matrix is, you will always solve it in this running time. What will happen here is that actually our running times will depend on like how bad our matrix is or how good it is, but that will be the problem. But the gain will be that actually, if the matrix is simple, you will get significant improvements. Okay, so this will be like a double-edged sword. The other thing that actually will be very nice is actually the computational model that we will, like the only way we will interact with this matrix will be actually in a very simple way. Namely, the only thing that we will ever want to do is just multiply a vector times our matrix. Okay, so action with A is only via a matrix vector products. Okay, so essentially all I really need to do is just an oracle that given a vector y returns to me A times y. Okay, I don't even need the direct access to the matrix A. Okay, and this is actually very, very nice for many reasons. One of the reasons is that essentially this takes advantage. So this is able to exploit sparsity, right? Because exploits sparsity. Because what happens is that the running time to do this essentially is just the number of non-zero entries of A. Okay, so if the matrix is sparse, this takes just like this always takes only as much time as the number of non-zero entries. So if the matrix is dense, it's still n squared, but if matrix is sparse, it's O of n. Okay, and so this will be automatic. You don't even have to think about it because your algorithm will only interact with your matrix in this way. Okay, so that's one more reason why this will be a good idea to do it. Okay, so let's try to talk about that. So before we do, we just have to deal with some technical things. So essentially, so far we only know that A is invertible. Okay, which really means that like it's linear algebra, so we should really think about matrices as just eigenvalues. So what it means is that all the eigenvalues of this matrix, they are non-zero. Okay, that's what invertibility means. But actually, some of them might be negative. And again, it doesn't mean that we cannot solve the problem, but it will become a difficulty that as you will see in a moment. So actually, still, I claim that without loss of generality, I can assume that A is not only invertible, but is actually PSD, so it's just positive semi-definite. So essentially, or actually positive, which means that all the eigenvalues are strictly positive. So there is no negative eigenvalue. So how can we do that? Well, essentially, all that really we have to see is that whenever you have a matrix that is not PSD, what you do instead, you try to solve a matrix like the system. So you have system AX equal B, and then what you do, you just left multiply by A transposed. Okay, as long as everything is invertible, this doesn't change. Like there is still only a unique solution to the system, and this is the solution you're looking for. And now this matrix over here, well, as we know, if I multiply two matrices, essentially they have exactly the same eigenspaces, because I just transpose one and the other. So essentially what happens is that this thing actually becomes, okay, and by the way, this is also symmetric. Okay, so essentially now this is symmetric and also PSD, because essentially the eigenvalues of that are just the square of the original eigenvalues. So essentially everything becomes positive now. Okay, and now now you can say, okay, but this sounds like cheating, because now I have to compute the product of A transpose times A, but that's actually the beauty of this oracle model. So in this oracle model, I just need to be able to multiply by this matrix, and actually I can just do it very easily, because I just, whenever I need to compute this thing, I first multiply, do this multiplication, and then I do this multiplication. So there are just like two vector product multiplications. So essentially, I don't really there is no need to ever do any matrix multiplication. Okay, so that's already one more convenience of this oracle model, that you can actually do this kind of composition and not pay anything really. Okay.
Will it still be sparse?
Well, essentially, the matrix might not be sparse, but your multiplications still will be very fast. Your multiplication will still take.
All right.
So that's the whole beauty of the trick. That yes, the A times A transpose might be not sparse at all, but you never need to compute it explicitly because you have this factorization. So you can just compute the only thing that you need, namely this vector product, like matrix vector products in time that is just proportional to the sparsity of the original matrix. So that's why this is so beautiful.
Sure. What is written in parentheses of what?
Oh, this is a NNZ of A, so number of non-zeros. Okay, so now we know that our matrix is PSD, so things become easy, or at least nicer. So now, let's just talk about how, we want, as you said, we will not get the exact solutions right away. We will actually just get better and better solutions. So we have to be careful about how we, how we measure errors. Okay, so we actually have to be explicit about this, because if you don't have the optimal solution, what is the right error measure? So there will be two actually alternative error measures. So the first one, I will call it it's kind of the left-hand side error measure. So essentially, if I have a solution X, then its error E of X will be exactly, it will be exactly, I just want to get it right, so I don't, there is a sign thing that I never get right. So essentially, I just compute, when I have my solution, right? In general, if I had exact, this what would mean for X to be optimal solution, that this thing is 0. So now there are two ways I can measure this, so this is essentially the error, right? Sorry. I will talk. So essentially this just tells me how much I differ from the optimal solution. Okay, so when I look at the solution space and I ask myself how close I am to the solution space, so this is the left-hand side error. Okay, but there is also another way of measuring your error. When you actually don't care about how far you are in the solution space, you just ask yourself, how far is what I will get if I multiply A times X, how far it is from what the target vector is. Okay, and this is of course the same as just saying that this is X star minus X, right? Because A times X star is B. Okay, we know that. Okay, so this is the right-hand side error. And of course, you know, when I'm at optimum, both these errors are 0. But as I'm not optimal, actually, these two errors can behave very differently. Okay, and depending on the circumstances, one is the better or the other is better. Okay, so this is this is, you know, these are the error measures. Okay, but now, you know, these error measures, they are actually vectors, right? So in the end, I would like to have one number that tells me how far I am, like how big my error is. So essentially, I just need some norm to measure my error in. Okay, and of course, natural norm to use here would be just Euclidean norm. Okay, I just look at the L2 norm of my error, and that's sort of like, you know, clearly if it's 0, I'm done, and as I'm reducing it, I'm clearly making progress. However, what turns out to be more convenient here in this context, like a more natural notion of norm, is actually A norm, when A is exactly the matrix we are trying to do, and is defined as just, you know, the square root of, so the norm of some vector x is exactly x transpose A x. Okay, so this is just a general PSD norm that is given by this matrix A. So matrix A is PSD, so it actually provides a metric via this. Provides the norm via this definition. So clearly, if A was the identity matrix, this would be just Euclidean norm that we know, the way we know it. But actually, well, usually A is not a identity matrix, so this is something different. It essentially rescales the space according to, you know, the eigenvectors and eigenvalues of the matrix. We will come back to this in a moment, but for now, this is just like, you have to trust me. This is the right norm to measure the error in. Okay. So now we know how to measure errors. So now the question is, okay. So but like, you know, how do we compute our solution? Okay, so essentially, yes, we know how to measure it when we have it, but how do we go about computing our solution? Well, essentially, and this is again the beauty of continuous optimization that you might not yet see fully, but, you know, hopefully you will start seeing, is that actually you already know how to do it. Like essentially, once you know gradient descent algorithm, there's always a way of doing it, like it's obvious to you. So all you have to do, you just have to, you know, formulate your problem as a unconstrained minimization problem and solve it using gradient descent. Okay, so how would you formulate this problem as a continuous optimization, as an unconstrained minimization problem? Well, here is a very simple way. I just want to minimize over x because, you know, I just want to find solution. There is no constraint on that. What I would like to minimize is just the A norm squared, okay, and the 1/2 is just to get rid of some annoying scaling. It doesn't really matter here for the problem because it doesn't affect minimization, like it doesn't affect the optimal answer. And now what I want to minimize is just the left-hand side error of whatever I get. Okay, so essentially it's like kind of, you know, just state what you want, and magically you hope that this is exactly what you will get once you minimize this thing. Okay, so this is the problem you would like to solve. Does anyone see any problem with it? So just to remind you. Exactly. So we don't know what x star is. So essentially we have a function we want to minimize, but we don't know how to evaluate it, right? Because we don't actually know. We don't actually know what is, you know, for a given point. It seems we need x star to even evaluate it. So that's a great point. So let's just look at it a bit more closely. So essentially, what is 1/2 EX8 squared? Well, essentially, by definition, this is 1/2 times, well, A minus x star transpose A minus x star, right? This is just, I just like unroll the definition of the error and I unroll the definition of the A norm. Okay, nothing happened here. So now let's just multiply out x and x star here. So we will have cross terms. So this will be one term will be this. Okay. Then there is another cross term that I will write in a second. Then there are two. Sorry, like these are the diagonal terms. Then there are cross terms, which essentially boil down to I have x transpose A x star, and then the one more remaining diagonal term is x star transpose A x star. Okay, so this is the objective we are actually minimizing, and notice that actually it's not as bad as you would think it is. Okay, so what is that?
B.
This is just B, right? And what is that? Well, we don't know what it is. It's essentially the like 1/2 of the A norm of the solution, optimal solution. But the important part is that this is a constant. Okay, it doesn't depend. This term doesn't depend at all at what x is. So essentially, if instead of minimizing maybe directly this function, I essentially just minimize a function g of x, which is just essentially I just take everything that depends on x here. Okay. Okay. All right. Okay. Then what happens? Well, clearly I can evaluate this thing at every point. And the minimizer of that is exactly the minimizer of the original function. Essentially just adding some constant, even if I don't know what it is, doesn't matter for me, because in the end, all I care about are gradients anyway, and gradient, like this constant gets just cancelled out in the gradients. Essentially, like, you know, I can just focus on minimizing this proxy function, which is exactly the same function really that I want to minimize. Okay, so from now on, the problem we actually try to solve is this one. Okay. So, well, how do we solve it? Well, I already told you how do we solve it. There is no need to think here. Essentially, we just will use gradient descent. Okay. So, what will be the algorithm? Essentially, the algorithm will be, as we all know, so start with some solution. Let's say that the solution is just all 0 vector, as good solution as any. And then what you do in each step, t, what you do is essentially you compute the new solution, which is just your old solution, minus eta times the gradient of g, right? So, okay. That's the algorithm. I don't have to think here. Now, what is the gradient of g? Let's just work it out. Well, essentially, this is the gradient of this function. So when you do the computation, well, it's multivariate, but you will quickly get the gist of it. So essentially, what you will get is this will be ax minus b. Okay. So this is t. So essentially, what it really is. This is the right hand side error of my current solution xt. Okay, so all I am really doing is that essentially I am just whenever I want to improve the solution, I just push it in the direction of minus whatever is the right hand side error of my solution. Okay, this is actually minus thing because I want to add it. Okay, so that's essentially how I correct. In each iteration, I just take my current solution, I look at the right hand side error, and I just subtract it. I just actually add it to my solution. Okay, and clearly you see that in particular when I get to a solution where the gradient is 0, this actually means that this is a solution to the system. Okay, this means that x is equal to x star, right? So essentially everything is sane. That's exactly what we want to do. Okay? And additionally, one more thing here that essentially we don't really need to know, but it's useful to know, is that actually if I look at the Hessian, well, we will need it in a second, but not yet. Hessian of G. Well, the Hessian of G is exactly the matrix A. So this means in particular that this is like convex Okay, and actually, like, in a second we will look into this closer, because now, essentially we know we have an algorithm. We know that eventually it will get to the right solution. But of course the question is, what is the convergence rate? So how quickly will we actually converge there? Okay, and for that we already know from the last lecture. Again, all these things build on top of each other. We know from the last lecture that all we really need to do to figure it out, we just need to understand, what is the, beta smoothness and alpha strong convexity of G, right? But again, we know how to do it as well, because essentially, if we know that the gradient or the Hessian of G is equal to A, and we know that essentially, beta is the smallest eigenvalue, and alpha is the largest eigenvalue. Right? This is exactly what we essentially said last time, that this is how you can get beta and alpha. So essentially the condition number of this function is exactly like the largest eigenvalue divided by the smallest eigenvalue. Okay? And this is exactly, so this is, by the way, I defined it as a condition number of a function. But here, if you know numerical analysis, this is also a condition number of a matrix. Essentially, we have a PSD matrix. Its condition number is exactly the largest eigenvalue to the smallest eigenvalue. And this is exactly the same notion for this reason. Okay? So essentially, the resulting running time, again, we don't have to think, is we know the number of iterations we need is roughly kappa times log 1 over epsilon. Okay, so essentially after this many iterations, okay, we will get a solution that is, xt minus, okay, so like I will not define exactly in what way, because should I do it? Okay, so essentially what will happen is that the 1/2 e of xt, so the error as measured in the A norm will be at most epsilon. Okay? That's essentially what will happen here. Okay, so great. So, everything is nice, but like the running time depends on this kappa, which we don't know what it is. But before we think about that, what it can or cannot be, let's just actually get some geometric intuitions of why even it is coming here. Like essentially, for now, all of this just is here because it is here, because it came out of the math. But it would be nice to understand exactly like actually what does it signify, and is it a fundamental reason it shows up here, or is it just some kind of quirk of our analysis? Okay, so let's just try to do that. So to this end, notice that the function g, okay, if I look at the level set of function g, so I look at essentially all the points, so let's just think about like 2D, okay, and I want to just think of all the points that are actually have the same value of this function, okay. Okay, well, we'll think about this in a second about 2D. Let's just in general, we just think about level sets, okay. So all the curve in our space and where the function has the same value. Essentially, we realize that if I look at the set of, so essentially the set of x's such that g of x is equal to some r, okay. So this is like the level set corresponding to r. What it really will be is just the set of x's such that x minus x star, okay, transpose a x minus x star is equal to r, okay. But what is this equation corresponding to? Does anyone see? Yeah, It's exactly the ellipse, okay, centered at x star, and with axis, like principal axis given by the eigenvectors of A and its eigenvalues, okay, and principal by A, okay. So essentially in 2D, if you think of 2D, then essentially we have only two eigenvalues, and there are two directions that correspond to eigenvectors, and essentially the smaller the eigenvalue is, the more drawn out this direction is, the larger it is, the more squished it is. Okay, so now I can think of two cases. So imagine that I have like the kappa is pretty large, it's just much larger than 1. Okay, so it means that like in two dimensions, essentially one eigenvalue is much larger than the other. Okay, then the picture there, like if I start visualizing level sets, then the picture there will be something, so I will just like squeeze things so my principal axes are aligned with my normal axis. So somewhere here will be x star, okay? And now what will happen is that like this ellipsis will be very squished. So these are the level sets of the function. So again, this is the direction corresponding to, let's say, to lambda 2. This is the direction sorry, the other way around. This is the direction corresponding to lambda 1. This is the direction corresponding to lambda 2. Okay, so essentially they are very asymmetric. This is like a very squashed ellipsoid. While on the other hand, if I have kappa being close to 1, well, essentially then there is, I have essentially almost perfect circles. Okay, so essentially I just have something like this is x star. Okay, so these are the geometric pictures of of how these two cases look like. But now, why does it matter for the convergence of our algorithm? Well, essentially, you have to understand what is really our algorithm doing. So let's say it is starting somewhere here. So here is our x0. Okay, and now what is it doing? Well, it says, oh, I will take a gradient of this function. And I will just move in that direction. So what is in the minus direction. So what is the gradient? Well, gradient just corresponds to looking at the at the line that essentially is is tangent to this level set at this point, and just looking in the in the orthogonal direction. So this is the minus gradient direction. So what I'm saying is, oh, I will take this direction, and I will move in this direction for some step. Okay, but now. Well, now I am a new level set. I have to, I have to figure out what is the new direction. So I will, I will maybe move here, and then essentially I will just keep doing this kind of things until I converge. Okay. So now the thing to notice here is that essentially, if I have this very large curvature, then essentially, so actually this will be maybe more dramatic over here. Then essentially my direction of the gradient, like ideally I would like my direction of the gradient to tell me, to push me in the direction of the optimum solution. But when things are very squashed, actually my gradient direction is actually taking me somewhere else. It's essentially like misleading me. I'm not really shooting in the direction, like I'm slightly correlated with the direction of the gradient. I know that this angle here, like essentially it cannot be like too large. But it can be, really, but it can be very non-zero. Essentially, it can be quite significant. So essentially, I will need to do a lot of corrections, a lot of this zigzagging, until actually I get to the solution. Because I will have to refine my, my coordinates. I always will be overshooting, so I have to just zigzag my way over there. While, if I was on the perfect circle in particular, then I, no matter where I start, if I look at the tangent line, it will be almost perfect. It will be almost perfect predictor of where the optimum lies. So essentially what I expect to happen is that, I will maybe do like a couple of zigzags, but I very quickly will converge to the right solution. Okay? So this is exactly like, this is where this like approximating things by quadratic comes in. Essentially, when the condition number is very bad, it means that my predictors of direction of the optimum solutions are very bad as well. And I have to take many corrections until I get there. While if things are well conditioned, if a condition number is small, my predictors are very close to the right thing, so I very quickly get to the right place. Okay? So we see that this is actually something fundamental. It's not just a matter of us just analyzing things in the wrong way. This is really the truth. And you can run this actually probably like 4 lines of MATLAB code to implement this, and you can actually see how these things happen. There really is that's how these things behave. Okay. So these are the intuitions. And so now as I just to summarize. So far we know we can solve this linear system in roughly kappa times log 1 over epsilon iterations. And actually this is pretty awesome, right? Because we didn't have to do any work. The algorithm was obvious, the analysis was already given to us, and we are getting the solutions, right? We didn't have to do anything. But now you wonder, okay, so now we are theorists, and now we wonder, okay, clearly the dependence on kappa is crucial here, because it can be very bad, and somehow this will hurt us then. So the question is, can we even improve this dependence on kappa at least somewhat? So, so actually, is it the best dependence on kappa? We can clearly see intuitively that we have to have that the kappa has to come into play somehow, because of this potential ill-conditioning of the space. But does it need to be linear? Maybe it's logarithmic. Maybe it's, I don't know, a kappa to the 1/5. Who knows? What is the right way for it to enter here? Okay, so let's just take a look at that, and to understand essentially what's going on and if you could do better, let's try to actually understand what the gradient descent algorithm is doing from yet another perspective, namely from algebraic perspective. Okay, so let's just recall what was the sort of like so far we just provided the update based on how does the solution change, right? So we just said that this is like eta times gxt. So this is how the solution changes, and we already identified this, that this is essentially x of t plus eta times the right hand side error of t. Okay, that was the gradient update in the solution space. But now let's actually try to figure out how does the right hand side error itself change from iteration to iteration. Okay, so let's just do some very difficult math. Okay, so this will be just the right hand side error at the after iteration t. Okay, so what it will be? Well, by definition, it's just b minus a times t plus 1, right? This is this is just definition. So let's write it out. It's just b minus a. Okay, and I just plug in the definition from here, right? So I just have to plug in here xt eta r. So, and this is just essentially, I can just write it as r of t, right? So now essentially I can just do some algebraic manipulations, and what I can get here is that, okay, so what is b? Again, b is actually a times x star. Okay, so essentially what I'm really doing, let me just write it. So what I want to say is that in the end I am obtaining something like that. So let me just now figure out yes, what it is. Oh yeah, exactly. So essentially if I look at these two terms, sorry, okay, so I have, this is like a x star minus, oh actually I didn't need to do that, sorry, that's too early. So essentially what happens is that if I look at this and this will be exactly the the previous right hand side error, and then this I just multiply things times a times eta. So essentially I clearly have this this equality here, that essentially my, so, but this is very interesting. So essentially the way I get my right-hand error after the new step is I just take my old right-hand side error and multiply it by this matrix. That's essentially how this happens, and this matrix doesn't depend on, what is the step I'm taking. So if I unroll it, then essentially I will get that my error at time t plus 1 is exactly like taking this matrix to the tth power and applying it to my first error, but my first right-hand side error is exactly b, right? Because my first solution is 0. Okay, so essentially this just gives me the recipe for the error after t iterations. Okay, so now the nice way to view this kind of expression is actually to view it in the space of polynomials. Okay, so what it means is that essentially what I really did is the way okay, yes. So essentially, the way I got r to t plus 1 is I took a certain polynomial, okay, t in A, in the matrix A, and applied it to B. Okay, so essentially, this is a polynomial of the matrix. Essentially, this is just polynomial of the matrix, but what is this polynomial? Pt of y. Well, essentially, I can think of it as a univariate polynomial. So essentially, like just the way I obtain the matrix polynomial is just I just plug in for every occurrence of this univariate variable, I just plug in the matrix A. Okay, so this polynomial is essentially, okay, so it's essentially, well, what is here? So it's essentially a very simple polynomial. It's just 1 minus eta times y to the t. Okay, and now if I want to understand how my actual solution is after t steps, then again, by definition, this is, just let me make sure I get the definitions right. It's it's essentially, okay, so I know that this is xt plus eta rt. Okay, so essentially what it is sum over I from 1 to t eta e minus eta a to the I times b. So essentially, like I just unroll these things, like I just unroll this recurrence, and that's what I get. So essentially, in the end, I just get some different polynomial that I will call t eta, okay, in A, and apply to B, when the polynomial over here will be exactly sum over I from 1 to t eta 1 minus eta y to the I. Okay, so I'm just saying all that I really said here is that there is this polynomial that the way my algorithm gets its like TIF solution is by just taking this polynomial in the matrix A and applying to the initial vector B. Okay, that's all that I said so far. But this is actually quite interesting, because what happens now is that, let's just think what really happens. So essentially, so one interesting thing to know is that if I have my matrix A, okay, then I can view it like, essentially the most important basis for this matrix is just the eigenvector basis. Okay, so imagine that actually my description of my space is in terms of eigenvector of A. Okay, so in this representation, well, A is a diagonal matrix. Okay, it's essentially exactly like, lambda 1, lambda 2, up to lambda n. So it's because like in this basis, this very special basis that depends on the matrix A, it looks very simple. Like this is the key theorem of linear algebra, that essentially you can diagonalize a matrix and essentially just describe it in this term. But now what is even more cool, and this is the way this diagonalization is so important, is that if I look at any polynomial in the matrix A, then in this basis it has like extremely simple form. What it really is I just take my diagonal matrix, and I just apply this univariate polynomial, just coordinate-wise to each diagonal entry. So essentially, this will be exactly p of lambda 1, p of lambda 2, up to p of lambda n. This is exactly what this polynomial in A will be. Okay? And now, from this point of view, we see what is happening. So we know that our solution x. Okay. So what it is. So I know that if I apply this polynomial qt of eta to my matrix A, I will get a matrix in which each diagonal entry is exactly qt eta of lambda 1 up to qt eta of lambda n. Okay, and then essentially I'm multiplying this matrix times b, and I would like and this will be my x. Now the question is, what it is that I would like this matrix to eventually be. Okay, so what should this matrix be? So I actually, essentially, I would like to get some polynomial in A times B, and I would like to take some polynomial in A, multiply it times vector B, and get optimal solution x star. What should be, well, okay, it doesn't need to be polynomial. What should this function be? This q star. Okay, so what is the function of A that if I could multiply B times it, I would get the optimal solution? Sorry? Can someone speak up? So what is the answer?
Inverse.
The inverse, exactly. So ideally, I would like this univariate function to be exactly just 1 over y. Because then this would be just A inverse, and I would get the optimal solution. So essentially what I really would like to happen here is that somehow this matrix that I'm actually getting using a polynomial should somehow converge, should somehow try to approximate just 1 over lambda 1, 1 over lambda n, which is exactly the inverse in the diagonal basis. Okay? So this gives us a condition on what we want the polynomial, qt eta of yb. So essentially what we would like to have is that for every I, we have that qt eta of y, is qt eta. So we essentially care only about behavior of this algorithm on the endpoints, namely the eigenvalues. Okay? So what I would like is for every eigenvalue, this essentially is equal to 1 over lambda I. Okay, so I would like it to approximately be that. Okay, if I manage to do that, then it means that actually I already got a very good solution. Okay, and these are the only this n constraints is the only thing I care about in terms of what this polynomial does. But of course, the other thing that that is constraining this polynomial is the degree. So it has to be degree t, because essentially in the end I am only able, so essentially every power of t, well, I have to multiply times a this many times. So essentially if I want to have t iterations, I can the largest power of a I can use is essentially the tth power of a. So now sort of the optimization problem. So if I'm asking myself, okay, so what would be if I just could take a polynomial of degree t and compute it in terms of matrix A and apply it to my vector B, I ask myself, okay, so what is the best polynomial to use here? Yes. So first of all, let's try to understand what does gradient descent. What is the polynomial that gradient descent computes? So I already told you that the polynomial is q t eta of y is equal to the sum from I1 to t eta 1 minus eta y to the I. So does anyone know what this polynomial is? Sorry?
Just y.
No. It is not y. It is, but it's a.
Does it translate to something in eigenvalue?
Sorry?
Does it translate to something in eigenvalue?
Well, now it's univariate. So exactly, this is how it works on eigenvalues. So we want it only for like n eigenvalues to behave 1 over this eigenvalue, but like this is the polynomial we got out of gradient descent. Does anyone see what is this polynomial corresponding to? It's not an easy task. So in the sorry.
Geometric progression?
No, yeah, but like it's in language of polynomials, what it is. Okay, so essentially what it is. Okay, so let's just try to understand what we are trying to do geometrically. So essentially, here like, so here we have like the y. Okay, in the y space we have these special points like lambda 1, lambda 2, and somewhere here is lambda n. Okay, and now somewhere here is like the the inverse function, which looks something like that. And now what we would like to do, we would like to get a polynomial, okay, that somehow moves through like close to these points. Okay, so it's that for every of these interpolation points it is close there, but it should be of degree t. Well, so what would be if I gave you this question, what would be your first try? Okay, so if I just tell you, I just need to find such a polynomial. So what it will be your guess for doing it?
Probably interpolate the first 2 points.
Well, interpolating the first d point actually would be bad. That's actually an interesting idea, except the problem is that then you have, for every interpolation point, you have to pay with degree. So you will be able to only interpolate at most t points. And t, well, you want t to be much smaller than n. But that's actually a very good intuition, and we will get back to that. That's essentially like one way to do it is you can just use interpolation, because like it's a well-known fact that if I just provide you with n points, like I say at this n points the polynomial should be should have value of exactly that. I can achieve this by interpolation formula, but my polynomial will have degree of exactly number of points, because that's how many, in the worst case, that's how many essentially changes of direction you need to fit all these points.
Maybe least square.
Sorry? Well, yeah. So okay. So essentially, what I do. So what is really this polynomial doing? So first of all, I didn't tell you what eta is, but essentially, in the end, once you figure out what is the best setting of eta, you will get. Just to make sure I get it right. Yes, you will get that this is 2 over lambda 1 plus lambda n. Okay. This is just from smoothness considerations. Well, if you think what is the best setting, this is what you will get. But modulo that. What this polynomial really is actually a Taylor approximation of inverse around point 1 over eta. Okay, so if you set eta to be exactly that, what you really are doing, you are looking at this interval in which in which all the points you care about lie. Then you take the middle point. This is lambda 1 plus lambda 2. Sorry, lambda n over 2. And what you do, you just compute a degree t Taylor approximation of inverse function around this point. Okay. So it's I will not try to draw it. Like in the notes, I actually figure it. Like I actually compute coded it up, and you can see the drawing. How does this approximation look like? But like what will happen there is that essentially that this is like a very reasonable choice. Like this is something that in the retrospect is saying, oh, that's what I should have tried if I wanted to solve this problem. And the cool thing is that gradient descent figures it out on itself. It's like no one told him anything about, well, okay, you know that it uses Taylor polynomial in some sense because that's how we derived it. But in the end, it's really doing this like very non-trivial idea, just comes out completely automatically here. Okay? So essentially, and then when you do the calculations and you figure out, okay, so how big degree I need to get to essentially get good matching on all of the points that I care about, then essentially you will get this formula that says that gives you the kappa dependence being linear here. Okay? So far so good. So now Well, the question is, what is the question that we should all ask now? Well, the question that we all should ask always is, is it really the best way to solve the problem? Like, is it really the best polynomial we can use? It's definitely a reasonable polynomial to use. Is it the best one? And then you should quickly realize that maybe not. Okay, so the reason is that somehow, what is Taylor approximation designed to do? Like, it's optimal in some sense. What is the sense? It says it just tries to match the function the most in the neighborhood of the point around which you are doing it. But here we actually don't care that much about this particular point. We care about the whole interval. Okay, and so essentially, if we screw up towards the end of the interval, it's as bad as if we screwed up in the middle. Like, essentially, there is nothing special about the point in it, because I want to get uniform approximation on all of the points. So this tells you that essentially, just like focusing on doing your job very well on the couple of points means that probably you are not doing your job that well as you move away. Okay, so essentially what it means, and this is just if it makes sense, essentially instead of thinking of this kind of Taylor approximation, you want to think of Fourier analysis. Essentially, just thinking about things that sort of essentially that are small in an interval as opposed to just small around a particular neighborhood. Okay, and then essentially you can just go into this is a question in something called extremal theory, essentially the theory of polynomials, orthogonal polynomials. This is that you can just phrase this question as such, saying, okay, I need to match these points in this interval in such a way that my uniform error is at most that, and what is the best in terms of degree polynomial to do that. And then what you get, not surprisingly, some Russian name shows up, and there is Chebyshev polynomials, which essentially give you the optimal answer to this question. Essentially, they give you the tight answer of what is the right polynomial to use. Okay, and again, in the notes you have actually, it is explained more. But the bottom line is that then when you use Chebyshev polynomials, what you will get is that you will get from, this kappa log 1 over epsilon dependence to actually square root of kappa. Okay, so essentially you are getting this square root of kappa, and this is actually huge. So both in practice and in theory, actually, the reason that you can actually get something sublinear here is very important and very useful, and square root of kappa is particularly so. And you can actually show that in this framework, essentially, this is the best possible. That in the worst case, this is the best you can hope for, no matter what polynomial you use. And every gradient descent algorithm corresponds to a polynomial. So essentially, you can show that every gradient descent algorithm, in the worst case, cannot do better than that. And this actually has a profound consequence that I don't have time to talk about. So
could you remind, this is the number of iterations?
Yes, this is the number of iterations, which corresponds to exactly the degree of the polynomial we are building. Yes, there's this one-to-one correspondence that essentially, because we need t iterations to get the power of t, and essentially, once we know it, you can just always build your iterations to get this polynomial. So it's like the one-to-one correspondence. Okay?
And you cannot do better because there are examples?
Well, so you cannot do better in the worst case. But in the end, the question is really in the end, you only care about your particular eigenvalues. So if your eigenvalues have some nice structure, in particular, if they are concentrated, and I don't have time to go through it today, but in the notes there is an example when actually you can take advantage of the fact that you know something more about how your eigenvalues are spread, and then there are better polynomials. And actually you can mix in interpolation with Chebyshev polynomials to get something better. But in the worst case, if just all I told you is that my smallest eigenvalue is this, my largest eigenvalue is this is the best you can do. Okay? So essentially, so I am essentially essentially run out of time, but there's just one more idea I want to just tell you, is that is very important. And again, the notes are long, so if you need nighttime reading, that's a good reading to do. So essentially, just so far, I just told you, okay, in the end, you have this running time of square root kappa log 1 over epsilon, and whatever kappa is, in the end, you are still screwed. Right? Essentially, there is no, if it's bad, it's bad. It may be square root of bad, but it's still bad. So the question is, is there something something more that I can do? And it turns out that there is some technique that actually can save you, even in the case when the condition number is bad, as long as you understand, as the matrix has some special structure. Okay, and somehow, so the idea here is just the following. I will go like 5 minutes over time. Sorry about that. So let me just skip to the notes. Yeah. So imagine I give you my matrix A looks like that. Okay, so it's like how many zeros? Just to get it right. Yes. Okay, this is my matrix. You know, looks normal. If you compute its condition number, it will be really bad. So the condition number will be, well, around 1 million. Okay, because clearly you see in particular like somehow this to this, that's the ratio that you will get. But now, you know, so yeah, so if I just want to solve the system AX equal B with this matrix, even if I use my best algorithm, it will still take me like 1,000 iterations roughly. And this is like 3 by 3 matrix. So essentially, clearly we are not doing something right. But now, if you look at this matrix, you will like so here's the trick. The trick is called preconditioning. Is that somehow, if you look at this matrix, it has very bad condition number, but sort of for stupid reasons. Okay, so what I mean by stupid reasons, essentially, if I just pre-multiply everything, left and right side, by inverse of the diagonal matrix. So essentially, I just take the diagonal entries of this matrix. Okay, and I put zeros everywhere else, and I just pre-multiply both of them. What will happen is, of course, it's equivalently, I just need to solve this problem, this linear system. But what happens is that actually, if I look at this matrix together, if I look at D inverse times A, then this matrix has condition number that is close to 1. Okay? So what it means is that suddenly I went from a system that was like very ill-conditioned to a system that actually is very well-conditioned. And now I can apply my algorithm to that. And its running time, number of iterations, will be actually proportional to the new condition number, not the old one. So I would actually solve it very fast, even though the condition number was horrible to begin with. Okay? And this is like this essentially preconditioning technique is what makes solving linear system in practice actually practical. Because people come up with like different ways of finding good preconditioners for your matrix. So essentially what is a preconditioner is something that on one hand, it's sort of, you want P minus 1 approximate. So roughly you would like that P minus 1 times A is roughly identity. So it's something with good condition number. And on the other hand, well, you want multiplying by P minus 1 is fast. Okay? So what I mean by that, because of course I always, if I just take P to be A, then always P inverse times A will be identity, so it always will be very well conditioned. But then multiplying times the inverse of it is actually quite expensive. So by the way, this is just equivalent to just solving a linear system in P for some Z. Okay, so essentially I need to solve, like if I have a matrix P that I can solve linear systems in it very fast, and this P approximates the inverse of A reasonably well, then I'm in business. And actually I can use it to bootstrap my computation. Essentially what I really use, I just essentially change the space, I reparameterize my space, my ellipses, to be again very round, and then things actually converge very quickly. Okay, but just taking P equal A doesn't work, because then I have to solve the system in A anyway. So clearly I didn't make any progress. So the whole point is to find something simple, like here, a diagonal matrix that is almost approximates the matrix well, but it's very easy to solve linear system in because it's a diagonal system. Okay, so this idea turns out to be very powerful, in particular for Laplacians. So I told you that we can actually solve. So essentially, if you look at Laplacians, then the condition number in the worst case, like if I fix a graph and I look at Laplacians, if I look at Laplacian of graphs in general, simple graphs, then actually I can. What you will notice is that essentially the condition number can be as bad as n squared. which means that if I want to solve it even using my best algorithm, I get O of n iterations. So in the end, it ends up being m times n running time. Okay, so it says that even if I use this method for Laplacians, just in vanilla way, I will actually get mn like quadratic running time, which is not what I promised to you yesterday. So now the whole idea to get nonlinear time is that actually there are ways of preconditioning, like of computing Laplacians that essentially change the condition number to be like logarithmic. And then you indeed have this kind of a logarithmic number of iterations. So actually you get nonlinear running time. And again, this is a beautiful theory, how to get these preconditional Laplacians. Actually, the simplest one is essentially to use a Laplacian of a different graph, namely a simpler graph. For instance, like even taking something called Lodestar spanning tree. So a special type of spanning tree will already work. But there are, like in general, there's notion of ultra sparsification, like a sparsification, ultra sparsification, that allows you to essentially find simpler graphs that, for which you can solve linear system in quickly and use them to approximate your original graph, sort of to get very good condition numbers. So this is like a beautiful theory, and I gave you a glimpse of it in the notes. But this is essentially what makes much of the stuff that I was talking about yesterday, and I will mention tomorrow, actually work. This is sort of the key technical driver that makes it work. Okay, any questions?
The functional problem is quadratic, so why we can't use Newton method?
Well, because Newton method, that's a great question. So the Newton method, unfortunately, it would converge in one iteration, except iteration of Newton method corresponds to solving a linear system in the Hessian. And the Hessian here is matrix A. So essentially you are using, so really we are solving the problem that you need to even use Newton method. And then I would just maybe, I don't think I have time, but if you think about actually the way you get the exact max flow is by using Newton method. And then this is actually exactly the building block that allows you to implement Newton method to run fast. Okay, but that's a great question.
So we not want to work with Hessians.
Sorry?
We not want to work with Hessians.
Yeah, well, because we are exactly solving the whole thing we are doing. We are implementing one step of Newton's method. So essentially, because just if I wanted to compute like invert it directly, it would take super quadratic time. Any other questions? Okay, great, thanks.